Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos, Ugobela Maths. And without any further ado, let's look at this question paper that we have here. Okay, so in preparation of the prelim exam that we are going to write tomorrow, Gauteng, we have this preparatory examination from Free State Province because they wrote theirs earlier. So this is Physical Sciences Paper 2. It has been written recently, September 2024. The marks are 150 times 3 hours. We are told that this question paper consists of 13 pages and 4 data sheet. Then here we have our instructions and information. So obviously can go through all of this. And then let's just go to our multiple choice questions here. It says various options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question numbers from 1.1 up until 1.10 in your answer book. For example, 1.11, if you feel the option is E, you can give it as E. We know that our options here do not reach up until E. It's just an example that they're making there. The condensed structural formula of an organic molecule is given, right? They say is the molecule unsaturated, or B saturated, or C a straight alkane, or D a straight alkene. Now, looking at this here, we know that the brackets here, CH3, indicates a methyl branch, right? So this is a methyl branch. Now, the minute it has a branch, it can no longer be straight. So that means we'll eliminate C and D. Those ones are completely incorrect, meaning now we have to decide between A and B which one is correct. So let's check here. Remember, we said this indicates a branch. So if we have to draw the structural formula so that we can see everything clearly there, the C is bonded to the H, but then it carries a methyl branch. So that's the methyl branch there. Then followed by a carbon that has 2 hydrogens, then followed by a carbon with 3 hydrogens like that. So this here becomes a what? A saturated compound because it has single bonds between carbon atoms. So our correct answer here should be B. Right. Then we have a 1.2. It says, consider the organic molecule below. The IUPAC name of its functional isomer is. Now this here, looking at this, we can tell that this here is an ester, right? With the O here dividing the side for the carboxylic acid and then the side of the alcohol, right? So this ester here would be what we know as methyl ethanoate, right? Methyl ethanoate. Now they say the IUPAC name of its functional isomer. They want the IUPAC name, not of this one, but of its functional isomer. When we refer back to cake, because this is for the functional isomers, we know that the functional isomer of an ester is carboxylic acid. The functional isomer of an aldehyde is a ketone. So what is a functional isomer? We're looking for something that will have the same molecular formula, but different functional group. So meaning it must belong in the carboxylic acid group. Now, looking at this, the only carboxylic acids that we have are your propanoic acid and ethanoic acid. Those are the carboxylic acids. Now, it's a matter of deciding, is it propanoic acid or ethanoic acid? Now, remember, we must form a functional isomer. The functional isomer must also have 3 carbon atoms, as this ester here. So the ester here is C3H6O2, meaning that the same thing that we have to choose here has to go C3H6O2. Now, between ethanoic acid and propanoic acid, which one would be correct here? It is obviously propanoic acid because it has 3 carbon atoms. Prop means 3. So that means the correct answer would be B. Okay, So now we are fine. Option is B. Then 1.3 says, consider the following organic molecule. The correct IUPAC name is, let's check. So the whole thing here, remember, if we want to reach to that, let's try to draw it out using structural formula. So this is a carbon bonded to an H, and then it has two methyl branches. So we have CH3 there, and then again down here, we have CH3. And then this is carbon with a hydrogen here, hydrogen here. This is C with a hydrogen, but then also has a methyl branch as well. So CH, like that, CH3. Then we have this one here. This is CH3. Now let's come up with the name. So from here, we can tell that the longest chain is 1, 2, 3, 4, 5. Let's check here, 1, 2, 3, 4, 5. So we can say 1, 2, 3, 4, 5. So either way, we can choose our longest chain. Let's go with that. Right. But then remember, in terms of numbering, we must number from the side that is closest to the disturbance. If we say 1, 2, this is in carbon number 2, and also here 1, 2, this is in carbon number 2. So either way, we can maybe choose to name it from down here. So that's 1, 2, to number, meant to say 1, 2, 3, 4, 5. So the longest chain has 5 carbons, which is pent, right? But then let's look at the positions of our methyl branches. We have a methyl branch in carbon number 2, and then we also have another methyl branch in carbon number 4, which this should be 2,4-dimethyl, right? So look at what I'm doing. I'm not looking at the options. I'm trying to draw that out so that I see what matches up with the options. So I have 2, 4, but then this is dimethyl, and then the longest chain is pentane. So dimethyl what? Pentane. So which option is that? Option number C. Or letter C. Okay, then 1.4 says, while a chemical reaction takes place, the rate of the reaction, so now we can tell that we are now on rate of reaction. So the first three was on was on organic reactions. Now we are on rate of reaction. While a chemical reaction takes place, the rate of the reaction, does it remain the same or decreases because the concentration of products decreases, or does it increases because the concentration of reactants increases, or does it decrease because the concentration of reactants decreases? What happens to the rate of reaction? Now, the only sound explanation to this is that obviously because when the reaction is taking place, the reactants will have to decrease, then obviously even the concentration of the reactants will decrease. So D here would have to be correct, because if we say decreases because concentration of products decreases, that is kind of incorrect, considering that we are only looking at the forward reaction. And then does it increase because the concentration of the reactants increases? No, the concentration of the reactants does not increase, but then actually it decreases. Does it remain the same? In order for it to remain the same, in fact, what remains the same will be the rate of the forward reaction and the rate of reverse reaction, not just the rate of one reaction, right? So here they did not mention forward and reverse. So we'd only say remains the same if we're being asked about the rate of the forward and the reverse reaction. So the correct answer has to be D in that case, because this is not, we are assuming that they're not speaking about a reversible reaction. Then 1.5 says, consider the following hypothetical reaction, which this here is a reversible reaction. The activation energy EA for this reaction is 100 kilojoules per mole. For the reverse reaction, now the forward reaction is exothermic, being indicated by this. Now, for the reverse reaction, meaning the reverse reaction would have to be endothermic because this is a reversible reaction now. Will the EA be equal to 100 kilojoules per mole? Not quite, so this one would be wrong. And then will the EA be greater than 100 kilojoules per mole? This one would have to be correct because with an endothermic, we know that our enthalpy change is always greater than 0. And then also the fact that it has a higher activation energy because it is a non-spontaneous reaction. Endothermic reactions are non-spontaneous, meaning they need additional heat and a higher activation energy. So B here would have to be correct. C and D are definitely incorrect. So yeah. So your option here would have to be B, considering that your enthalpy is greater than 0, and this is a non-spontaneous reaction which needs a higher activation energy. Right, so that's your 1.5. Now 1.6, that is based on your acids and bases. They say write down the conjugate base of HClO4. So what would be the conjugate base of this? For 1.6, we will go with, if this is HClO4. Now, for the fact that they're saying conjugate base of this, it means that this is an acid here. So if we are to react it with water, then that means the H here will have to be donated, because if this is an acid, it donates a proton. So remember, an acid is a proton donor. So ClO4 minus, and then we will have our hydronium ion forming H3O plus. Right. So obviously looking at this, this would be the acid going together with its conjugate base, and this would be a base going along with its conjugate acid. So which one matches up with the options here? So that's C, ClO4 minus. Then done with 1.6. Let's check 1.7. So a solution of sodium hydroxide, let's check, is it A, tense bromothermal blue to yellow? Not quite. And then is it B, is it acidic? No, hydroxide can't be acidic. And then C, does it turn phenolphthalein to colorless? Not quite. And then is it D, is it basic? So D would be correct because sodium hydroxide, we know it to be basic. Right. Sodium hydroxide, in fact, is a strong base. So this would have to be basic. A solution of sodium hydroxide would be basic. So 1.7 is D. Then 1.8 says a piece of magnesium ribbon reacts with excess hydrochloric acid according to the following balanced equation. Which one of the following is an oxidizing agent? Which one is an oxidizing agent? Now, obviously, in order to find that, we'd have to check here. So this is 1.8. So oxidizing agent, let's see. We have our Mg here. And then if we are to break this one down here, this needs to be Mg2 plus, and then Cl minus, and then we have our H2 here. This is H plus, and then Cl minus. This is our Mg here. So let's break down everything. On this side, I'm going to break down. I have my Mg, it's a solid. And then if I break this one down, it's H plus. And then I have Cl minus. And then let me break down the ones here. They should give me Mg2 plus. And then the Cl there should just be Cl minus. And then here I have H2. So H2 is just like that. Now let's check which one is an oxidizing agent. Oxidizing agent undergoes what? Reduction. So which one is being reduced? Now if we can check here, reduce means that it has to decrease in oxidation now. It has to decrease in oxidation now. So let's compare. If I compare Mg to Mg2 plus on the product side, This is not a decrease in oxidation number. It's actually an increase in oxidation number. So this here would have to be oxidation. Now, with Cl, I have Cl minus on this side, and then Cl minus also on the other side. So this is just a spectator ion. So it's still the same. The oxidation number is the same on the left and on the right. Let's look at H+. We have H+, and then going to H2. Oxidation number here is +1, but the oxidation number of a diatomic molecule is 0. Now here we see a decrease in oxidation number, which means that this is reduction. So what did they say? Which one is an oxidizing agent? The oxidizing agent is the one that undergoes reduction, so meaning it is your H+. Which one matches up with that? It's option number C. Right. So you have to know how to break those one down into ions so that you can tell what is happening there. So option C is correct. Now let's check 1.9. It says in a galvanic cell, the Sol bridge is at A, responsible for the charge balance to be maintained in the cell. So the Sol bridge, or does it allow for the movement of electrons from one half cell to the other? Or does it allow the mixing of two solutions from different half cells, or is not necessary for the optimal functioning of the cell? Now, which one is the correct answer there? It is definitely A. It is responsible for the charge balance to be maintained in the cell. Remember, we say it maintains neutrality of the two half cells, right? It maintains neutrality of the two half cells. Okay, then we have 1.10 says, what is the energy conversion in an electrolytic cell? Electrolytic cell. So electrolytic cell, we know that it needs a power source. So definitely it's taking electrical energy to chemical energy. So which one matches up with that? Electrical to chemical has to be option A, right? So they try to confuse you there with electrical to mechanical, but we know anything that says mechanical in chemistry is not make sure, right? So it's only an option between A and B, but we know that it's electrical to chemical. So just like that, you have came to the end of your multiple choice questions, and that's how you would have that 20 marks in the bag. And then now let's start answering the questions, starting from your question 2. But then also remember the advice. It is much better for you to start with your questions, question 2, all the way to question 9 before you start answering your multiple choice questions, because multiple choice questions can take a lot of time, especially if you are trying to figure out those questions there and trying to remember the concepts. So rather go to questions whereby you can easily accumulate marks. And then when you are left with about 15 to 20 minutes, you can try to answer this multiple choice questions here. Then, okay, let's go to question 2 now. Okay, so we have question 2 on organic chemistry. It says the letters A to E in the table below represent organic compounds. So as we can see, we are given all these organic compounds here. And then having to apply the strategy that I taught you is that the first thing that you want to do is identify the homologous series of each of these compounds given here. So looking at this, we can tell that this is just methane. It belongs in the alkane homologous series. This is propyl ethanoate, so we know that's an ester. And then here we have OH, indicating that this will be an alcohol. And then propanol, this indicates that it's an aldehyde, looking at the suffix here. And then E is 3.3 difluoro 2-methylpentane. So because of the halogen here, fluorine, then we know that this is a haloalkane. So it becomes very easy to answer these questions after you have done that. So 2.1 says write down the letters representing a compound with the general formula CnH2n plus 2. Now we know this to be the general formula of an alkane. So that means which letter here represents an alkane. It's just a matter of checking here and saying that's A. Right. Which letter now represents a haloalkane? And then we just go here, it's E. Right. And then 2.1.3, a functional isomer of a ketone. Now remember, what are functional isomers? Whenever we are talking about functional isomers, you think of cake. So carboxylic acid is a functional isomer to an ester, and then aldehyde is a functional isomer to a ketone. Now we have an aldehyde here. They're asking us a functional isomer of a ketone. So we know functional isomer of an aldehyde is a ketone. And then therefore our answer here is supposed to be D. Right. So see how quickly you answer those questions after you have done that. For compound C, they say write down the type of alcohol it is and give a reason for the answer. So we go to C. Remember, when they're talking about type of alcohol, they're saying, is it primary, secondary, or tertiary alcohol? So all you have to do is come in here to the carbon that is attached to the OH and then count how many other carbons is it attached to. So looking at this, we can see that the carbon that is bonded to the OH group or the hydroxyl group is bonded also to 3 other carbon atoms. So which makes it a what? A tertiary alcohol. So for 2.2.1, we say we have a tertiary alcohol. And then reason for that, the carbon bonded to the dash OH, right? So the carbon bonded to the OH group is bonded to 3 other carbon atoms. And then voila, that's how you have it. Right. Then 2.2.2 says give the IUPAC name. So to give the IUPAC name, let's gather our information here. So obviously we have to first identify the longest chain. Now you have to be very careful of this question here. So looking at this, we can see that this is a chain 1, 2, 3, 4, 5, 6. But then you have to contrast it with another one here. This is 1, 2, 3, 4, 5, 6, 7. So the longest chain, remember that your chain can also bend like that, right? When it goes in here, this is not a branch because it bends over there. So this becomes here the longest chain, right? And then you have to start numbering from the side that is the earliest disturbance. So if you can count from this side, that's 1, 2, 3, 4, 5. We only have a disturbance in carbon number 5. But now when we have to count from this side here, that's 1, 2, 3, and then we have a disturbance at carbon number 3. So that means in numbering, we have to start numbering from the side that is closest to our methyl branch in our functional group, right? The substituents. Then the name thereof of this one will be what? So 1, 2, 3, 4, 5, 6, 7. The longest chain is hept. So we are going to have a hept. So, okay, the first thing, obviously, we have to indicate the branch here. So the branch is in carbon number 3. So this is supposed to be 3-methyl. And then hept dash, okay, alcohol, 3-methyl heptane, because it's an alcohol, it has to be heptane, and then it's in position number 3, all. So the hydroxyl group is in position number 3. So the 3 here indicates the methyl branch, which we have here. So that's our methyl branch in carbon number 3. But also in carbon number 3, we have the hydroxyl group. So 3-methyl to indicate that we have a methyl branch in carbon number 3, and heptane-3 to indicate that we have a hydroxyl group in carbon number 3. Then all indicates that this belongs in the alcohol homologous series. So the suffix is all. Okay, right. So that would be the IUPAC name. Now they say name of its functional group. What is the functional group? What is the name of the functional group of an alcohol? We know it to be what? Hydroxyl group. It is very important that you know the functional group names, right? So for an alcohol, we say it's hydroxyl group. And then for an aldehyde, we say it's a formyl group. And then for your carboxylic acids, carboxyl group. And then for your ketone, it's carbonyl group, right? So make sure that you know those. For compound B, now they say write down the structural formulae of two organic compounds it is formed from. Compound B is an ester right there. So we know that an ester forms as a result of mixing an alcohol and a carboxylic acid. So whenever we have a reaction of an alcohol and carboxylic acid, we have an ester followed by a byproduct of H2O. But since now we have propyl ethanoate, we know that the propyl here is coming from the propan 1-ol because you must always have a primary alcohol to form an ester. And then the ethanoate here is coming from what? Ethanoic acid. Right. So we have propan 1-ol and ethanoic acid, and these are the two organic compounds. But note that what did they say here? Structural formulae, right? So they were not just concerned about the names, they wanted the structural formulae. Now let's draw the structural formulae of that propan 1-ol. This is prop 3. So 1, 2, 3. And then just have your OH over there. And then fill in your hydrogens. Fill in your hydrogens. And then it's chai. Ethanoic acid, eth means 2. So 1, 2. And then you can have at the first carbon here, your functional group. And then here you cannot put another hydrogen because 1, 2, 3, 4. It's 4 bonds around carbon. And then there you go. So that's the propan 1-ol, and that's the ethanoic acid. Then 2.3.2, structural formulae of the functional group of its functional isomer. This question was on steroid, ne? Structural formula of the functional group of its functional isomer. Now note, this here is an ester. Remember, we are still considering compound B. Compound B is an ester, but then let's go back to cake for functional isomers. We know that the functional isomer of an ester is a carboxylic acid. So in other words, we must draw the structural formula of the functional group of a what? A carboxylic acid. Right. So what is the structural what is the functional group, the structural formula of the functional group of a carboxylic acid? We know it to be like this. So you just draw that skeleton there with the OH and then just indicate that there needs to be a hydrogen there. So and then there we go. We have it like that, right? So obviously the dash here indicates that you can then fill in your what you call your hydrogen atoms if there's a hydrogen atoms, or you can still fill in your carbon, right? So this here is called what? A carboxyl group. So this is what we call a carboxyl group, right? It's the functional group of the carboxylic acid. So, okay, right. Now write down the structural formula of compound E. Dang. Compound E, we know that in order to draw that, we need to first figure out how many carbons must we have there. Pentane on the longest chain, we must have 5 carbons. So 1, 2, 3, 4, 5. Now, difluoro, we have 3 difluoro, and then there's a methyl in number 2, carbon number 2. So let's start with that methyl branch there in carbon number 2. So I'm choosing to make this carbon number 1 here. Shucks. And then hydrogen. So in carbon number 3, we have fluoro. So fluorine here, and then fluorine there. And then let's fill in our hydrogens. Fill in our hydrogens like that. And then that's it. That's how you have a 2-methyl 3,3-difluoro. Remember, the reason we are starting with fluoro here, it's because of the alphabetical order rule. So F comes before M, so we have to say 3,3-difluoro-2-methyl pentane, right? Because F comes before M. So it's always the substituent there, or the halogen, before the methyl branch, right? So, but then that's 1, 2, 3, 4, 5, right? So 2-methyl, and then you have your 3,3-difluoro here. Difluoro because there are 2 of these fluorines. Okay, nice. Done with 2.4. Let's now move. So we have, that's not the final question there. Okay, we have 2.5. It's saying compound A undergoes complete combustion, right? We know combustion is when you take an alkane and then react it with oxygen gas, and it always produces carbon dioxide and water, and then you have to just balance it. So they already balanced it for you. As you can see, the 2 there and the 2. So that was for the purpose of balancing. Then during the combustion, now we know that sometimes you might have to balance that on your own. So I've talked about the CHOR method, where you have to balance the carbons first, then hydrogens, and then oxygens. Then during the combustion, 2.75 kilogram, right? Note this. In Gauteng paper 1, you were given your mass in grams, which you needed to convert to kilograms, because this is what you need to understand. When it comes to P1 physics, paper 1 physics, your mass should always be in kg. So if they give you in grams, you convert to kg by dividing by 1000. But in paper 2, which is your chemistry, you need to understand that your mass should always be in grams, right? So here, if you are given in kgs and then you want it to go to grams, you need to multiply by 1000. So that's the difference between these two papers. You have to understand the difference in terms of mass in physics and in chemistry is that in physics, we need it in kgs, but in chemistry, we need it in grams, right? So, okay, that means we have to first deal with that 2.75 there. So our mass should be 2.75 multiplied by 1000, which if we multiply that one, that's supposed to be what? 2,750 grams, right? And then obviously we want to calculate the mass of CH4, which is this one. So we'll make use, remember this 2.75 gram is for carbon dioxide. So if this mass is for the carbon dioxide, meant to say, that means you can use it to calculate the number of moles of carbon dioxide. So we know that our stoichiometry, remember a calculation question that appears in question 2 cannot be that difficult. It's just basic stoichiometry, or they will ask you to do empirical formula. I think there was one question in June whereby you had to do empirical formula. Then this is 2,750 over the molar mass of the carbon dioxide. So carbon is 12, oxygen is 16, but then there's 2 oxygens in carbon dioxide. So which makes it 32, 32 plus 12, that's 44, right? And then if you punch that into your calculator, you have to get 62.5 mole, right? So now that you have the number of moles, your basic stoichiometry says after calculating number of moles, then number 2 is to compare the molar ratio. So we'll say what is the ratio of CH4 to the ratio of carbon dioxide. And from our balanced equation, we can tell that it is 1:1, which means that also the number of moles of the methane should be 62.5 mole, because a same ratio means they have the same number of moles. Now, to calculate the mass, that means I can say mass of CH4, and then this from this formula here, I'm supposed to say N multiplied by the molar mass. And then my number of moles, 62.5. The molar mass of CH4, that's C is 12 and then plus 4. That's 16, yes. And then 62.5 times 16, that's 1,000 grams, right? 1,000 grams, which if you are to just write it in kgs again, that's just 1 kg. But then you can leave it as 1,000 grams, since we said that our mass is needed in grams in paper 2. Right, then that's how you were supposed to solve that one. Easy peasy calculation, nothing difficult to it. Question 3 now, physical properties. It says the boiling points of 4 organic compounds at a specific pressure are compared. Then define the term boiling point. So you have to know all the definitions from boiling point, vapor pressure, and melting point. So 3.1 boiling point, we say this is the temperature at which the vapor pressure of a substance, the vapor pressure of a substance is equal to the atmospheric pressure. Yizo, dango. Then, yeah. Then, okay. That's it. Now, they say consider compounds A to C and then fully explain the trend in boiling points from A to C. So now let's check A to C. A to C, we can see that we are dealing with compounds that are in the same homologous series, right? Same homologous series. And then if you've been watching my videos, you now understand the method to explain if you are given compounds that are in the same homologous series. That's ISCE, right? Where you talk about the intermolecular forces that are there, identify the type of intermolecular forces. Now, since all this belong in the alkane homologous series, we know that they have London forces. So you see, I'm just analyzing. And then we speak about the surface area or the structure. Now, obviously, from here, we can see that we are busy creating more branches. And then if we are creating more branches, that means we are compromising the surface area. So the surface area becomes smaller. Then we have to compare the strength of the intermolecular forces as we increase the branches and then decrease the surface area. And then we then have to speak about the energy required to overcome the intermolecular forces. So I is for the type of intermolecular forces, S is for the surface area. So this is the structure of where you get marks in terms of explaining this. And then C is for compare strength of intermolecular forces. And then E is for energy required to overcome the intermolecular forces. So that's basically the ISCE method. Okay, so now that means this is how we are going to explain that. So that means from A to C, 3.2.1, from A to C, the number of branches increases, right? And then, which means this results, so this results in a resulting in a decrease in surface area. In a decrease in surface area. Now, let's mention the fact that the compounds from A to C have London forces. They all have London forces. Strength of the London forces. Strength of London forces decreases from compound A to C. Why? Because the more we are increasing the branches, we are decreasing the surface area. So obviously, if the surface area decreases, that means there is less dispensation of the London forces, right? So strength of London forces decreases from A to C. And then less energy required to overcome the intermolecular forces or the London forces from compound A to C. Thus, the boiling point decreases. Thus, the boiling point decreases from A to C. So as we can observe here, in A, there is 6, B, 28, and then C, finally 10. Because now you are busy decreasing the surface area. And then when you are decreasing the surface area, the strength of the intermolecular forces weakens. And if the strength of the intermolecular forces weakens, there is less energy required to overcome those intermolecular forces. And therefore, the boiling point decreases because intermolecular forces, they are directly proportional to the boiling point. So the weaker the intermolecular forces, the lower the boiling point. So note that the ISCE method, we have that. So we have identified the London forces right there. We have identified that these compounds have London forces. We have spoken about the structure by saying from A to C, the number of branches increases, resulting in a decrease in surface area. Then we did mention the strength of London forces. So strength of London forces decreases from A to C. And then we have spoken about energy, less energy required to overcome the London forces from compound A to C, right? That's the boiling point decreases from A to C. That's it, 4 marks. Okay, now, which compound will have the highest vapor pressure? Now, the answer to that lies in the relationship between, note that here we are only given the boiling point, but now they're asking about the vapor pressure. So the answer to that lies in the relationship between boiling point and vapor pressure. We know that boiling point is inversely proportional to vapor pressure. So that means the one with the lower boiling point will have to have a higher vapor pressure. So in other words, from the table here, what we are looking for is the one with a lower boiling point, but then this is between A to C, right? Remember 3.2 says consider only compounds A to C. So that would have to be what? Lower boiling point is 10. So this is compound C. So you can say it's compound C, or you can just say it's 2,2-dimethyl propane. So why? 3.2.3, it has the lowest boiling point. It has the lowest boiling point, and therefore will have a higher vapor pressure because of the relationship. Boiling point is inversely proportional to vapor pressure. Okay, then let's check now. 3.3 says compound D and E are compared. So D and E, so note that D is what we call, that's pentanal, it's an aldehyde. And then aldehydes mostly have what we call dipole-dipole forces. And then butanoic acid is a carboxylic acid. And then carboxylic acid, we know that it has what? Hydrogen bonds. And it has two sides, even two sides of hydrogen bonds. Right. Then they say compound D and E are compared. Is the boiling point of compound E greater than, smaller than, or equal to 103 degrees? Fully explain the answer. Now, obviously, knowing that hydrogen bonds are stronger than dipole-dipole forces, and the relationship between intermolecular forces and boiling point is directly proportional, then we know that since it has stronger intermolecular forces, it must have a higher boiling point. So our answer to that is that it needs to have greater than 103 degrees. So greater than 103 degrees Celsius. Right. Then our explanation, if you can check there now, we are comparing compounds that are in different homologous series. And then I said, if you are comparing compounds in different homologous series, then you have to consider to use the method ICE. So in ICE, you identify the type of intermolecular forces in both those compounds. Then you compare the strength of those intermolecular forces. And then finally, you speak of the energy required to overcome those intermolecular forces. So we're going to say pentanal. So pentanal has dipole-dipole forces. Whereas butanoic acid has hydrogen bonds, right? Has hydrogen bonds. Now, this should be able to give you 2 marks because you have identified that pentanal is dipole-dipole forces and butanoic acid is hydrogen bonds. So this statement alone should be able to give you 2 marks, right? And then from there, you need to say that hydrogen bonds. So this is where now we are comparing. Hydrogen bonds are stronger than dipole-dipole forces. Which means more energy is required to overcome the intermolecular forces, in compound or in what? In butanoic acid. In butanoic acid. Thus it will have a higher boiling point. Now, so 4 marks, right? So you see, once you know those methods, it becomes very, very simple to tackle that. So dipole forces, hydrogen bonds. Then to compare the strength, that should be a mark. More energy is required to overcome the intermolecular forces in a butanoic acid. So that should be a mark right there. And then obviously this is just you concluding. Thus it will have a higher boiling point. Okay. Then nice, we have that 4 marks. Then 3.4 says, is the comparison in question 3.3 fair? Right, in question 3.3. So is it fair? Definitely. So yes. And then the reason for that, they say, explain the answer to question 3.4. Now, this is based on they have around the 2 compounds, okay? The 2 compounds, D and E, have a relative molecular mass. Now we can compare them because they're within the same mass, right? So it might not be exactly the same, but then they have a relative mass. So if we can check pentanol, pentanol will have a C5 and then H10 and then O. But then butanoic acid will have C4 and then that should be, so it's C4H8 and then O2. Now let's compare here and see if they are around the same mass. So if we can just go and check, we have carbon, that's 12. So let's start by this molar mass of this C4H10, C5H10O. Then this should be 5 multiplied by 12 plus 10 plus 16. And then this is 5 times 12 plus 10 plus 16. So it should give us 86 grams per mole. Now let's compare it with the mass of this one. That's 4 times 12 plus 8 plus 2 times 16. So it should give us 4 times 12 plus 8 plus 2 times 16. This is 88 grams per mole. Now 88 grams per mole and 86 grams per mole, that's a relative molecular mass. So it's not the same, but then it's around the same molecular mass. So that is fair. If you compare compounds that are within the same weight or the same mass, meant to say, then you can say that it's a fair investigation. So the two compounds have a relative molecular mass. Okay, so that's it with your question 3.5. So for 14 marks, so now if you can check, we now have 22 plus 14. We are down at 36 marks, right? From just answering these two questions on organic chemistry. Now that means we have to answer this one here, question 4, organic reactions. If we add that 17, we are at about 53 marks, right? So we know that organic chemistry is about 30%, more than 30% of your paper. So you know organic chemistry, then you are at a position whereby you have a pass already in physical sciences or chemistry. The flow diagram below shows the steps in the preparation of an alcohol from compound Y, which is saturated hydrocarbon, right? Saturated hydrocarbon. So hydrocarbon is the one that only contains hydrogen and carbon atoms only, right? Then 4.1 says explain the term halogenation. So halogenation, this is a reaction of a halogen with an organic compound. So a reaction of a halogen with an organic compound, that is called halogenation. So halogenation, because we are trying to create a haloalkane. For reaction 1, write down the one reaction condition. So let's check a reaction 1 here. Now, note that they're saying this is starting from compound Y, which is a saturated hydrocarbon. Now, let's remind ourselves of these reactions. We have S, 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 which means this is what? Saturated to saturated. So saturated to saturated is substitution. Now, what is substitution reaction? Basically, if I'm going to be moving from an alkane and then I go to a haloalkane, or vice versa, it's haloalkane to alkane. So this can happen in that form or that form, right? So let me just use this arrow here for reversible. So if you are moving from an alkane to haloalkane or haloalkane to alkane, there is a substitution reaction because it's a saturated compound to another saturated compound. Or it can be a haloalkane going to an alcohol or alcohol back to haloalkane. That can also be an example of a substitution reaction. right? But then we have USA, which means unsaturated to saturated, is an addition reaction, right? So we normally say this is a reaction whereby we are breaking double bonds. So in addition reaction, we are breaking the double bonds. Unsaturated to saturated is addition. So that means all these reactions must start from an alkene going to either an alkane or a haloalkane or an alcohol. So basically, if you are moving from an alkene, breaking the double bonds of an alkene, and then you have a single bond alkane, single bond haloalkane, single bond alcohol, then that's an addition reaction. Now, obviously, if you are breaking this one to an alkane, then you have what we call a hydrogenation reaction. And then if you are breaking it to a haloalkane, this is where you have a halogenation reaction. Or sometimes it can be a hydrohalogenation reaction. And then if you are breaking it to an alcohol, this is where we say you have a hydration reaction. Right. So it's very easy to remember those. Then SUE is what? Saturated to unsaturated is elimination. Now this means here, you are actually forming the double bonds. You are actually forming double bonds. Right. So if you move from saturated to unsaturated, basically it's just the opposite of addition reaction. So that means in this case, you'll be moving from an alkane, a haloalkane, and then an alcohol, and you are going to what? An alkene. So it is just the opposite of an addition reaction. Now, if you are moving from an alkene to an alkene, this is where we say you are actually having a dehydrogenation reaction. Remember, this was hydrogenation. Now it's D, meaning that you are eliminating the hydrogens now. If this is, you are moving from haloalkane to alkene, now this is what we call dehydrohalogenation, right? Okay, so a small diversion there, but then let's go back to our question. We have question 4. It says the flow diagram below shows the steps in the preparation of an alcohol from compound Y, which is a saturated hydrocarbon, right? And then we said this one here should be an alkane, right? And then because hydrocarbon, it only contains hydrogen and carbons. Then for this reaction here, they're saying what's the one reaction condition? So in 4.2.1, we know that the reaction condition always for substitution reaction is you need sunlight or heat. Then in 4.2.2, they say the formula of the inorganic product. So remember, this is a substitution reaction. And then we know that with substitution reaction, we are only taking a hydrogen atom here and replacing it with a bromine atom. But then the hydrogen will react with one bromine atom that is in here. So the inorganic product should be HBr. Remember, inorganic means that it does not contain carbon. Does not contain carbon or is not an organic compound. So HBr is an inorganic product there. Now 4.3 says for reaction number 2, where is reaction number 2? There we go. Write down the balanced equation using condensed structural formula. Right. Okay, so now this is a compound Z going to this. And then remember, we did note that the compound Z that will form here has to be a haloalkane because what we are performing here is a halogenation reaction. So that means here, the compound that should form is, looking at this one, we can see that it forms ethanol. So that means we've been using ethane here, and then this ethane became a haloalkane, still having 2 carbon, and then became an alkene, and then became that, right? So that means the reaction that we should have there is of C. So the first thing that I want to do, I know that it says condensed structural formula, but then I will try to draw it first using our structural formula, and then I will condense it afterwards so that you understand. So this is our hydrogens here. And then we have our bromine, because only one of the bromine will come in here. And then this must react to form an alkene. So because it's moving from a saturated compound to an unsaturated compound, then we know that it is elimination, right? Now, elimination happens if we want to react this with sodium hydroxide, because now we are performing what we know as a dehydrohalogenation reaction. Now, always pay attention to that. I always advise you in terms of that reaction there, to say that if there is a reaction that they want you to draw there, to show either using structural formulae or condensed structural formulae, it will be the dehydrohalogenation reaction, or it will be the hydrolysis reaction, or it will be the dehydration or hydration reaction. So they really, really love to give you those ones. Right, so now if you reacted with sodium hydroxide, because this is an elimination reaction, we need to eliminate the bromine and also the hydrogen there. Right, so note that. Now when we eliminate that, a double bond is now formed in between those carbon atoms. Right, so a double bond is formed like that. But then what happens to this Br here? It reacts with the sodium there, because obviously the Br here will become an N-ion, which will be attracted to the positive ion here, the cation, so NBr. But then the H here is a cation that will be attracted to this OH minus here, which will give us a byproduct of water, H2O. Right, so that's how you are supposed to go about with this one. And then also note that this sodium hydroxide here has to be concentrated. So concentrated sodium hydroxide, because it's elimination. And then, okay, that's it. But then I'm not done, because I'm supposed to show this using condensed structural formula. So condensed structural formula, that's my answer. This is CH, I'm going to say CH3, and then followed by what? CH2, and then I have Br. Then this will react with sodium hydroxide to give me, the product is now what? CH2, then followed by what? CH2. You see, so basically with a condensed formula, you are just simply telling me the first carbon here is bonded to how many hydrogens. This carbon here is bonded to how many hydrogens, and also the halogen there. Then again here, this carbon bonded to 2 hydrogens, this other carbon bonded to 2 hydrogens. And then plus my byproduct, obviously, plus NABr plus H2O. So basically your answer should look like this. And then also indicate, so you can indicate that this one needs to be concentrated. Then other than that, it's awesome. Now we know that the base that you can use here, you can even use potassium hydroxide, which is a KOH. You can also use lithium hydroxide. That's definitely your choice. For someone who chooses to use potassium hydroxide, it's also okay. And others that choose to use lithium hydroxide, that's also okay. But then basically, your answer should look like this. Right. So, okay, let's now move. They say write down the name of reaction 3. What is reaction 3? Now we are moving from an alkene to an ethanol, right? Alkene to ethanol. So this here we are moving from alkene to a saturated compound. So unsaturated to saturated, that's addition. So it's an addition reaction, but then we need the name, right? So it's an addition reaction. Now we can just say addition. They did not ask us to be specific, but then if we were to be specific, if we reacted with water, we know that's a hydration reaction. So that's a hydration reaction. In reaction number 5, C3H6O2 is formed when ethanol reacts with compound X. Hallelujah. Remember, I always state this. Your esterification questions will be the last questions there because esterification is not part of addition, substitution, or elimination. It's a reaction on its own, right? So which is why you see an increase from the number of carbon atoms there. So remember, we were having 2 carbon atoms all the way, but then here we now have 3 carbon atoms. So obviously this tells you that we have reacted 2 homologous series. Now, they say write down the IUPAC name of compound X. What is compound X? If this is already ethanol, then the compound X that will give us a total of 3 here, it has to be what? Obviously, so eth is 2, then we have to react it with compound X that has only 1 carbon atom. So which makes it what? Methanoic acid. Methanoic acid. Right. Then now you can see if we say that ethanol plus methanoic acid, this is where we have our ester here, which should be ethyl methanoate. Right. But then we were only required to write this. So 4.6 says write down the name of reaction IV. We already know esterification. So check your exam papers. You will always see this trend. Then 4.7, using structural formulae, write down the balanced equation for this reaction. Also another one that you should note. So of all the reactions that they will want you to draw the structural formulae or the condensed structural formulae are this. So it's either it's your hydrolysis, which this one is a substitution reaction, and then they will want you to draw for hydration, which is an addition reaction. So you can go and check this. And then it can also be dehydrohalogenation, which is an elimination. Now, sometimes they can ask you to draw the one for dehydration, which is also elimination, right? But then most definitely, they will also include esterification. So if you can know these reactions very well and know their reaction conditions, then you are at a much better chance to excel in your organic reactions. So note that trend. This is the trend that I've kept on observing while doing much more past exam papers. Okay, using structural formulae, write down the balanced equation for this reaction. So remember, we did mention that we will be reacting our ethanol with methanoic acid, and then this should give us ethyl methanoate. So now it's just a matter of drawing all this in terms of our structural formulae. But let's not forget our byproduct, H2O, because it should be balanced. Then ethanol is our alcohol. It's a primary alcohol, obviously. And then methanoic acid, only 1 carbon. And then we have OH, and then close it off with that hydrogen. Now, looking at this, the OH must always come from the carboxylic acid, and the H must come from the alcohol. So this will give us, so let's note that we need our concentrated sulfuric acid here as our catalyst, right? So it's very important that you show that reaction condition up there as well. And then there we go. So obviously now we are left with this oxygen here, which will be the divisor between the alcohol side and the carboxylic acid side. Then plus the H and the OH, that's the inorganic product that forms. So there we go. We have our ethyl methanoate. So ethyl methanoate. So that's the balanced equation using structural formulae. Awesome. Okay, so we have question 5. We have now entered the big 3. So we know in chemistry, we know that question 5, 6, 7, yeah, those ones are the big 3. That's where you need to really pull in your chair in your exam paper and start to really focus. So which is why my strategy is always you answer question 2 all the way to question 4, which is your organic chemistry. You jump the big 3, and then you go to question 8 and 9, which is your electrochemical cells. And then within the last hour, you can look at your big 3 questions, which is your question 5, 6, and 7. That is basically my strategy that I'm going to give to you to just implement while you are still practicing and see if it's going to work for you. How does it work in terms of saving you time and also sparing that energy for you to then have to use that energy to look at these questions, but also making sure that you have used most of your time to collect marks which are freely given in the exam paper. Then grade 12 learners use a reaction of calcium carbonate with excess hydrochloric acid to investigate the relationship between concentration and the rate of reaction. The balanced equation for the reaction is as follows. They say they conduct the experiment twice, each with a different concentration of hydrochloric acid. A decrease in the mass of the flask and the content is represented in the table below. So as we can see all that, then 5.1 says write down the name of the apparatus used for measuring the mass. Now we obviously know that has to be a mass scale, right? So they're using a mass scale. Then 5.2 says write down the name of the limiting reagent. Now, if they've already said that HCl is in excess, we know that if we have 2 reactants, one has to be in excess and the other has to be limiting. So if we are already told that this is an excess reagent, then it goes without saying that obviously this here has to be a limiting reagent. So the name of that, remember they said name. So we should write calcium carbonate. Calcium carbonate. And then 5.3 says define the term rate of reaction. So we know we are saying this is the change in concentration of a product or reactant per unit time. Right. So that's the definition for reaction rate, the change in concentration of products or reactants per unit time. Now you can see you already have 4 marks from that. Then 5.4 says for experiment 1, calculate the rate of reaction in mole per second. It's very important that you check the SI unit that they want you to use in the first 30 seconds. Now in the first 30 seconds, that will be represented by the time from here to here. So this is in experiment number 1. So that means this is where we should focus. So this is the block in which we should find our data here. And then, okay, so the first thing, obviously, we have to, because this is in mole per second, we are given the masses here. We have to first find the number of moles that reacted from 0 to 30 seconds. So number of moles reacted would have to be what? I would have to say, number 1, let me subtract the mass. So initially we had a mass of 270 grams. And then after 30 seconds, we have a mass of 268.4 grams. So that means to get the mass that reacted within the first 30 seconds, we would have to subtract this. This gives us 1.6 grams. Now at this point, we can then calculate the number of moles that reacted by using the formula mass over the molar mass. Then if you say 1.6 divided by what? Remember, this was for what? The mass that was recorded here is the mass of carbon dioxide. Remember, with reaction rate, we are always recording the reaction rate using the gas that escapes, right? So the only gas that we have here is carbon dioxide. Always put that in your mind, right? We are always using the gas in order to determine our reaction rate. So the rate in which the gas escapes, that tells us of our reaction rate. Then this is 44, the molar mass of carbon dioxide. 1.6 divided by 44, it's going to be 0.036 and then 36. Let's round off to at least 5 decimal places. So 0.03636, that's the number of moles within the first 30 seconds that reacted. Now reaction rate, we know our formula RR is equals to change in the number of moles over the change in time. Remember, as much as when we define here, we say rate of reaction is the rate of change of concentration of reactant or product. It is not always that we have to use concentration. If we have to calculate in terms of our number of moles, then we can say change in number of moles. If we have to calculate in terms of volume, we will say change in volume. So there are various formulas for rate of reaction. You can also have rate of reaction is change in V over delta T, or rate of reaction is change in concentration over delta T. So it's based on what you are actually trying to calculate, or what SI unit did they use in terms of calculating the rate of reaction. Now, in this case, we can see that our rate of reaction needs to be in mole per second. So obviously, how will you come up with mole per second? It's change in the number of moles over the change in time. Now, at this point, we did find the number of moles that reacted between the first 30 seconds. So that's 0.03636 minus 0, obviously. And then our delta time there has to be between here. So that's 30 minus 0 as well. And then if we calculate here, this is going to give us 1.21 times 10 to the exponent of -3 mole, right? So obviously mole per second. And then if you wrote it in normal form, I think it's 0.0021 mole per second, right? But then obviously some of your calculators will just write this in scientific form. Okay, so that's how you were supposed to get that 5 marks there. So 2 marks for having to be able to calculate the number of moles, and then the rest of the 3 marks will be found from having to substitute in here and get the correct answer there. So 5 marks like that. Okay, then 5.5 is saying, in which experiment did the learner use a higher concentration of hydrochloric acid? So which experiment? Let's check now. Obviously, that will be based on the rate of reaction. If we can check here we said here between the first 30 seconds, 1.6 gram had already reacted. But then here, within the first 30 seconds, only 1 gram had disappeared, right? So obviously, because here we are observing a higher reaction rate, so there's more of the carbon dioxide gas that escapes the reaction vessel within a short period of time than compared to experiment number 2. Then that means for 5.5, we are going to conclude that obviously in experiment 1, that means more HCl was used. Remember, the greater the concentration, the higher the reaction rate, right? So concentration and the reaction rate are directly proportional. If your concentration is higher, then it will lead to a higher reaction rate. Then 5.6, we are supposed to use it to use collision theory to explain that the answer to question 5.5. So why do we say it's experiment 1? Now, this is how you put it. Increasing the concentration or a higher concentration results in more particles per unit time, or per unit volume, meant to say. Then increasing the concentration results in more particles per unit volume. So there will be more particles in the reaction vessel. And then this will lead to what? This leads to more effective collisions per unit time. Per unit time. So you see your keywords there. Once you have more particles, you can see that you mentioned that there will be more particles per unit volume. You mentioned that there will be more effective collisions per unit time, right? So those are your keywords there. Those are the things you need to include if you want marks, right? Then obviously, this leads to more effective collisions per unit time, thus increasing the rate of reaction. Increasing the rate of reaction. So we'll end up having a higher reaction rate as compared to this one, because we have used, as compared to experiment number 2, because we've used a higher concentration of HCl. Okay, so that would be your 3 marks there. So like that's increasing the rate of reaction. Okay, so in the bag, we have 13 marks already from answering that. So we can see from this question that reaction rate is not that bad. You might need to just practice a few of those calculations, a few of some stoichiometry questions there in order to be able to answer those rate of reaction questions. And then sometimes there's those kind of questions whereby you have to apply your stoichiometry for like 6 marks, but then those are things that if you practice, you can end up mastering. Okay, then let's now move to question number 6, which is the enemy of most of your chemical equilibrium. Question 6 says ammonia gas is produced by pouring nitrogen gas and hydrogen gas in an empty container and allowed to react in a closed container according to the following balanced equation. The graph of the rate of forward and reverse reaction is indicated below. 6.1.1 says define the term chemical equilibrium. So you say chemical equilibrium. This is where the rate of forward reaction. So always include the word rate. Do not say this is where forward reaction is equal to reverse reaction. You need to say this is where the rate of, right? The rate of forward reaction is equal to the rate of reverse reaction. Then 5.6.1.2, identify the change made at time B, right? Now we know that if both of these graphs increase like this, there's no sharp increase like this one's here. This always represents an addition of a catalyst. So all of this are based on just having your notes, knowing your notes here. So this is an addition of a catalyst. So if you can just have a study guide document, the one that I recommend is the self-study document from DBE. It has all these graphs and then explains what is happening when it's like that. And then when it's like this, what is happening. So that's basically your note. Then there was a temperature change at time C while the pressure was kept constant. How did the temperature change? Write down only increase or decreased, right? So we have this here. And then looking at C, we can tell by the rate of reaction there is a decline. And then if we know most of these reactions here are what we call an exothermic reaction. So this here we know it to be an exothermic reaction. And then they say now there was a temperature change at time C while the pressure was kept constant. How did the temperature change, right? Only increased or decreased. Then we are going to say it was what? Decreased. Decreased. Now let's explain why decreased. You will know that again from your notes that this here, the broken line, always starting up here, always represents the forward reaction. So let's explain that. And then the bold line here obviously have to represent the reverse reaction. So if you want to tell which one is the reverse and which one is the forward, the one that always starts from the origin here and then increases like that is always the reverse reaction. And then the one that starts from here and then decreases like that is always the forward reaction. Again, that is from your notes. Then there is a decrease and then there is an increase. This is reverse reaction, let's indicate. And then what we have here is the forward reaction. Okay, so now let's check what happened at C here. At C, they say is the forward reaction endothermic or exothermic? Now, this is an exothermic reaction. Exothermic reaction. Use Le principle to explain the answer to question 6.1.3. Now, this is explanation. In C, we say a decrease, according to Le, we know that a decrease in temperature, favors an exothermic reaction. An exothermic reaction. And then the forward reaction is favored. The forward reaction is favored. How do we say that the forward reaction is favored? Look at the reverse reaction. At C, there is a huge decline on the reverse reaction. But then what happens to the forward reaction? We can see it there, just smoothly gliding over there, right? So this decline here indicates that the reverse reaction was not favored. And then what was favored is the forward reaction. So the forward reaction is favored. And then obviously, the rate of forward reaction decreases less than the reverse reaction. So in a case whereby we are decreasing temperature, we know that in the system, it causes a decrease in the rate of reaction, because when we talk about rate of reaction can be increased by increasing the temperature. But then here we decided to decrease the temperature, which we must see our rate of reaction declining here. But then because when we observe the graph for the reverse reaction, there is a huge decline, which means that the reverse reaction was not favored in this case. But then for the fact that the forward reaction only showed a small decrease. Now, the small decrease is telling you that the rate of reaction was affected, but then it was not affected that much when it comes to the forward reaction. So that means the forward reaction was favored. So if the forward reaction was favored, and then we see that this was a decrease in temperature, this tells us that our forward reaction has to be exothermic, because the only reaction that is being favored by a decrease in temperature is an exothermic reaction. So I hope all that makes sense, right? So temperature was decreased, forward reaction was exothermic, and the explanation is that a decrease in temperature favors an exothermic reaction. The forward reaction is favored. The rate of forward reaction decreases less than the reverse reaction, indicating that the forward reaction was favored. Okay, let's now proceed. So our question 6 is not done. We know that you are not done with chemical equilibrium if you haven't seen anything that says calculate Kc. Then the decomposition reaction of nitrosyl chloride, NOCl, is represented below. At a temperature of 50 degrees Celsius, 4 mole of NOCl is placed in a 2 dm cube container. At equilibrium, it was found that 0.9 mole per dm cube of NO was formed. Then 6.2.1 says define the term reversible reaction, right? So another definition right there. So reversible reaction is when the product can be converted back to reactants. So when the products can be converted back to reactants, we say that is a reversible reaction. Then there is the devil right there. 6.2.2 says calculate the value of Kc at 50 degrees Celsius, right? So, okay, we know that for that one, we need our rice table. Let's go. So first thing you want to confirm if all of this should be in the Kc calculation. So they're all guesses. So yep. And then there we go there. Okay, so let's start with ratio. And then we have initial number of moles here. We have change in the number of moles. We have a number of moles at equilibrium. And then we will have equilibrium concentration. So initial mole change in moles, and then equilibrium number of moles, and then we have our concentration at equilibrium. C is equals to N over V. Now we have NOCl followed by NO and then Cl2. What's the ratio of the NOCl? That's 2. And then what's the ratio of the NO? That's 2 as well. And then here we have 1, right? So these are ratios. And then let's check. Initial at a temperature of 50 degrees Celsius, 4 mole of NOCl is placed. So 4. This is the only reactant, right? So that means initially we don't have any number of moles for the products because the reaction will start with only the reactants in the sealed 2 dm cube container. Then they say at equilibrium, it was found that 0.9 mole of dm cube of NO was formed. So at equilibrium, we found that NO, so the NO is which one? Is this one here, 0.9. So 0.9 mole per dm cube was formed. Okay, nice. And then what else are we given? So that means we can use this one to find the equilibrium number of moles. So by the side, let's say C is equals to N over V. Concentration is 0.9. And then N, our volume is 2. So if we say 2 multiplied by 0.9, that's 1.8 mole. So we have 1.8 mole here. But then these are products. So in order to find the product here, we know that for the product, if the forward reaction is favored, we always say it's it's to find the equilibrium, it's I plus C, right? So in order to find the one at change, then we understand that here from 0, the change was 1.8. The one that was produced is 1.8. Therefore, that's why we have 1.8 at equilibrium. But at this point, this is where now we use the ratios. So this is a ratio of 2 and that a ratio of 2. So that means they have to share the same number of moles. But then because these are reactants, in the reactants, we normally say, so for the reactants, if the forward reaction is favored, to find the ones at equilibrium, we normally say it's I minus C. So the change here has to be negative. So minus 1.8. So now we can get the ones at equilibrium by saying 4 minus 1.8, which should give us 2.2. So it's very crucial that you understand this. If the forward reaction is favored on the reactants, if you want to find the ones at equilibrium, take the initial minus the one at change. Remember, the change block, we always say that it relates to the ratio here. So every time we are trying to get the ones on change, we will use the ratios. Now, the ratio here is 2:1. So meaning to find this one, we can simply say 1.8 multiplied by 1 divided by 2. So see that, cross multiply it, 1.1 times 1, then divided by 2. So this should be half of that, which is plus 0.9. Why is it plus? Remember again, to find the ones on the product, it's I plus C. But this only applies if the forward reaction is favored. If the reverse reaction is favored, then this whole thing is an opposite. The reactants would have to add and the products would have to subtract. Because now if the reverse reaction is favored, that means we are using up the products in order to form back the reactants. So this is 0 plus 0.9, which is 0.9. Now to calculate the concentration right there, that's 0. It's supposed to be 0.9 divided by the volume here. Remember, it's number of moles over V. So 0.9 divided by 2, that should give us 0.45 mole per dm cube. Again, here, if we want the concentration at equilibrium, that should be 2.2 divided by 2, number of moles over volume. Then that should give us 1.1 mole per dm cube. At this point, now we can calculate our Kc. So at this point, can then say, let's calculate our Kc. So which should be Kc. Okay. So our Kc should be so this should be Kc is equals to the products over the reactants. So products are your Cl2 and then also your NO. But then remember, what you have as a ratio there now becomes an exponent. Over the reactants, that's your NOCl. And then what you have as a ratio now becomes an exponent. Now you just substitute in this. So your Cl2 minus, that's 0.45. And then your NO, that's 0.9. And then square over your NOCl is 1.1. So that's 1.1 square. Then obviously at this point, you just need the aid of your calculator. And then you have your Kc is 0.33. Then just like that, you have your 7 marks. You have your 7 marks. So where would you find your marks? Having to use the ratio to find this. Okay, you had your 0.9 here, and then having to use the ratio to also find that. And then having to subtract this so that you find the 2.2. And then also here, having to find all of this here correct should be a mark. So now you have 4 marks. And then the other 3 mark, we know it's coming from the Kc. So substituting in here, then substituting in the values, and then finding your Kc value. Right, so all in all, we have 7 marks. All right. So kwamele ubujimile to get those ones. Just practice, practice. Practice makes perfect. Then, okay, let's go to our friend, question 7. We also know that when it comes to acids and bases, that final question there for about 7 or 8 marks there. Yeah. That one, it will deal with you. Very nice. Then 7.1, according to the balanced equation below, a dilute solution of HCl is used in titration against an ammonia solution. Then 7.1.1 says define the term hydrolysis. Now, hydrolysis, what is it? So in definition, we'll say this is a reaction. So do not think of hydrolysis in terms of the organic chemistry. The hydrolysis in here, we say is the reaction of salt. The reaction of salt with water. The reaction of salt with water. Now 7.1.2 says, will the final solution be acidic or basic? Right. Now looking at this here, this is HCl. We know HCl here to be a strong acid. Right. Then obviously this will impact this thing to be what? Acidic. So this will be acidic, mainly because hydrochloric acid is a strong acid. Now they say write a balanced chemical equation that explains the answer to question 7.1.4. So if we take the NH4 that is produced here, remember we have to break this one down here. This will be NH4 plus and then Cl minus. So we'll try to prove using this whether this was acidic or basic. So all you have to do is ionize this, and then you have your ammonium ion. So this is NH4 plus, and then react that with water. React that with water. Now, obviously, what must happen here, the NH4 plus ion should act as an acid, and this one is a base. So if it acts as an acid, it will donate its hydrogen atom to become ammonia now. And then the hydrogen that was donated to H2O will now make this to be H3O plus, which as we can see here, according to Arrhenius theory, an acid is a substance that produces hydronium ions when reacted with water. So the fact that we are producing hydronium ions there is evidence enough that this reaction here was acidic, or that solution there was acidic. So because we have hydronium ions being produced, that means the final solution was acidic. Okay, then for the above titration, 25 centimeter cube of 0.1 mole per dm cube, NH3 solution is titrated against 40 centimeter cube hydrochloric acid. Now, is hydrochloric acid a strong or weak acid? We mentioned it. It's a strong acid. So from your notes, we already know that HCl, you don't play with it. It's a strong acid. It will ionize you completely. Then a strong acid. Then explain the answer to question 7.2.1. So we know it ionizes completely. It ionizes completely in water. Now you can add to form hydronium ions. Right, but then as long as you mention it ionizes completely in water, that's correct. Right, so you can say that acids and bases is kind of friendly when it comes to those questions whereby you are just explaining stuff. The only difficult questions when it comes to acids and bases is that 7 or 8 mark calculation that is usually there. But then you can still score marks if you know your concept of acids and bases. If you can answer why something is a strong acid or a weak acid, you can tell what makes it to be acidic or what makes it to be basic according to Arrhenius theory, then you should be able to collect some marks there, right? because even if you are calculating right now, we haven't really done a lot of calculation or any calculation at all. But then note, we have 2, 1, 3, and then that's 6 marks. We have this 1 mark here. We have this 2 marks. So 6, 7, 8, 9. Write down the name of the indicator that is mostly used for this reaction, right? Now, for a reaction whereby something is acidic, we know that we use what? Methyl orange. Now, also, this one is something that you can see from your notes. If you can just study your notes from grade 11 acids and bases, then you should know that question. Or ask a grade 11 learner, they will tell you. Then explain your choice of indicator. This is because we are doing a titration of a strong acid with a weak base. So NH3 here is a weak base. So now you understand why this whole solution was acidic. We are reacting a strong acid with a weak base. So obviously, the whole reaction has to be acidic. Right. Then that's it. We have explained that. Now, that is in the bag, that is in the bag. Now, obviously, we have talked about 3-mark questions: formula, substitution, correct answer. So it should be easy to calculate the number of moles right there, because all you are going to say is C is equals to N over V for 7.2.5. Now, are we given the concentration? They say calculate the number of moles of NH3 in 25 centimeter cube of ammonia. And then here for the above titration, 25 centimeter cube of 0.1 mole NH3. This is the ammonia we are talking about. So we are given volume, we are given concentration. But then we know this volume, it's only a matter of dividing it by 1,000 so that we have it in dm cube. So, but then our concentration is 0.1, and then N, our volume 25 divided by 1,000. So this is supposed to give us 0.025. And then if we cross multiply here, our answer should be 2.5 times 10 to the exponent of negative 3 mole, right? And then also if your calculator is writing it in normal form, you have 0.0025 mole. So that is also the same answer there. Okay, so 3-mark question. Now, if you have all of that, that means your only problem here is maybe minus that 8 marks. So 23 minus 8, you still have 15 out of 23. That's a decent mark. But then if you still want to fight the good war, you can still do that question 8 and maybe try to answer it to some extent so that you walk out with at least 2 or 3 marks out of that 8 marks and not just leave a blank space there. But then for the ones that are strong enough to answer that, obviously they will answer that. Then calculate the pH of the final solution if the concentration of the original HCl was 0.1 mole per dm cube. Now, for the fact that they are touching on HCl, that means the concentration must be based on the HCl. Now, we did mention that this is a strong base. So also, for the fact that they're telling us final solution, that means HCl will remain in excess, meaning that the NH3 here is actually a limiting reagent. So what are we going to do? Remember, in 7.2.5, we calculated the number of moles of NH3, which is the number of moles that reacted of NH3. And then let's compare it to the number of moles of the HCl. Now, obviously, this involves us having to go back to the balanced equation here, and we find that the ratio is 1:1. Now, a ratio of 1:1 means that the number of moles of NH3 that we just calculated in 7.2.3 should be the same number of moles of HCl that reacted. That did what? Reacted. So we calculated 2.5 times 10 to the exponent of negative 3 mole. Now, these are the ones that reacted. But then now, If we are to use that, remember, this is about concentration. Let's find the concentration that reacted from that. So concentration of HCl, that's N over volume. The number of moles is 2.5 times 10 to the exponent of -3. And then the volume of the HCl, where we given there, yes, 40 centimeter cube. So we can say 40 divided by 1,000, that's 0.04. And then we find the number of moles reacted is 0.0625 mole per dm cube. If it gives you in a scientific notation, it's also correct. I think it's about 6.25 times 10 to the exponent of -2. And then at this point now, this is the concentration. But then they said the original HCl concentration was 0.1 mole per dm cube. Now that means if we want to find the number of moles, the concentration of HCl in excess, or the final, right? Note that in order for us to find the final, we have to have the concentration initial minus the concentration reacted. Right. The initial concentration, they told us 0.1. But the concentration reacted, we calculated 0.0625. Right. So when you calculate that one, you are getting 0.0375 mole per dm cube. Mole per dm cube. Now, if we have the concentration, we know that we can calculate the pH, right? Because all we need is the concentration for the pH. But then note the fact that HCl is a monoprotic base. So that means the concentration of HCl to the concentration of the hydronium ions that it produces has to be 1:1. So hydrochloric acid only produces one hydronium ion. So that means also the concentration of H3O plus in this case should be equal to the concentration of the HCl in the final solution. So 0.0375 mole per dm cube, right? Then at this point, it's voila, calculate your pH. Then pH is equals to negative log times the concentration of the hydronium ions. Then simply substitute that concentration there, 0.0375. And then press umshinwe, and then you get 1.43. Remember, pH has no SI unit. So do not put any SI unit there. It's just that. So 1.43. So, okay, now you can say that it's a fair question. It's not that difficult. You just need to know the steps into answering those acids and bases question. So here, but then let's talk marks. If you were able to show the ratio here and that they will have the same number of moles, then you could have got at least 1 out of 8. And then if you were able to come to this point here, whereby you were able to divide this one out and find this answer, that's also 1 mark. If you were able to subtract here, that should also give you another mark here. Oh, also here it's substitution and the correct answer. So from doing this and also doing that, that's 3 marks already. Then having to find the difference between here, that's the 4th mark. And then we also have having to compare the ratio in here. That's the 5th mark. And then having to come to a point whereby you show this, that's another mark. And then here, 1.43, that's a mark, right? So what was the total mark? 8 marks. So I think, so here they gave out 2 marks here. They gave out 2 marks for having to subtract and find the answer. So 1, 2, 3, 4, 5, 6, 7, 8. Right. So it's just a matter of checking where you could have pushed it and then calculate how many marks you could have got out of 8. So if you're able to push it up until this point, at least you have something, 3 marks. If you're able to see that you need to subtract initial minus reacted, then you also have this, and then obviously you found your answer there. So you could have been at 5/8. Then if you are then able to make this conclusion here and then calculate your pH, you have all the 8 marks. So that's how you were supposed to go about answering that question. So you see it's a heavy one, 23 marks. But then you need to be very strategic in terms of answering these questions. Make sure that you always understand that it's about collecting marks and not having to answer each and every question that you see there, right? But then again, when you are practicing, know where to focus on based on whatever strong points that you have, and then also the weak points that you have. If you feel that all the other topics, you have them in the bag, and then it's only just that calculation for the pH, then you can just spend most of your time trying to practice that, and then up until you master that. Okay, and then now let's go to our question 8, where things are now a bit eased up. Okay, so now we have question 8 on galvanic cell. It says the following balanced chemical equation represents a reaction taking place when a galvanic cell is in operation under standard conditions. The initial reading on the voltmeter is 0.14 volt. 8.1 says write down 2 standard conditions under which it operates. So for our 8.1, we can say this operates under the standard condition of concentration of 1 mole per dm cube. And then we can also mention that we should have a temperature of 25 degrees Celsius. But then here we can see that we have a chlorine gas. So also we must have a pressure of 101.3 kilopascals. So you can write any 2 from all these 3 here because they only said 2 standard conditions. But then all standard conditions are concentration, temperature, and pressure. Okay, note that you don't say pressure if you don't see any gases. The reason we have this one, pressure, it's because there is a gas there. So always be careful to check if there are any gases. And if there are no any gases, do not mention pressure as a condition because that is only applicable to gases. Okay, 8.2 says for this cell, write down the name or formula of the electrolyte that can be used in the salt bridge. Now, this is coming from your notes. So usually the type of salt that they use there is potassium nitrate. Potassium nitrate. And then KNO3. As to why they use that, don't ask me. Then 8.2.2 says, give the formula of the reducing agent. Now we have to understand what is a reducing agent. This is a substance that undergoes oxidation, right? So note that reducing agent makes sure that the other substance is being reduced, gains electrons, but in turn it is being oxidized. Now we go back to our equation and try to find out between Cl and Au3+, which one is being oxidized. Remember, when we are looking for the agent, we have to check it here on the left-hand side, right? So between Cl- and Au3+, which one is being oxidized? Then this is Cl- with an oxidation number of -1. And then when it gets here, it's now a what? A molecule, a diatomic molecule with a charge of 0, right? Oxidation number of 0. But then with Au3+, this has a charge of +3. And then now when it gets to this side here, the charge is now 0, right? So it's now an atom. But then what is oxidation? Oxidation is simply an increase in oxidation number, right? So this is an increase in oxidation number. Now, which one has an increase in oxidation number? Meaning you are looking at the one whereby if you look at your number line, it will be moving to the right of the number line. So from -1 to 0, we can agree that if we have -1 here and then 0 here, this will be moving to the right. But then with +3 to 0, we are moving to the left, which indicates that we are gaining electrons. So Au3 plus is gaining electrons to Au. So that means this is actually an oxidizing agent, right? But then Cl minus is doing what? Is oxidizing. It is losing electrons and then loses that one electron and then goes to 0. So that means your reducing agent in actual fact is Cl minus, because this is where we see an increase in oxidation number from negative to positive. Okay, then our cell notation. Now, in order for us to come up with the cell notation, let's understand this galvanic cell that has been given to us. Now, most of the time I hinted to this galvanic cell here and I said this is a special galvanic cell. And then because we are used to the standard, it's standard, but then we are used to the one whereby we don't have any gases coming in there. So this is your Sol bridge like that. So what about this one? A lot of people are not aware of this kind of galvanic cell here, whereby we have our chlorine gas making way inside here. Now, because, why am I having this one here? This is the anode side. We have identified that Cl minus to Cl2, that's oxidation. And then we know according to NOx, red cat, where we have oxidation is our anode side. And then where we will have reduction is our cathode side. So this one from Au3 plus to Au, that's reduction. So this should be on the cathode, and then oxidation, this should be on the anode. So anode, it's Cl minus and Cl2. So that's why we have our Cl2 chlorine gas coming in here. And then right here, we will have our Cl minus. But then the one thing that you will note here is that we don't have any solid to act as an electrode, right? Remember, electrodes must always be solid. Now, because we don't have a solid on the anode side to act as the electrode, we now have to employ platinum, right? So if we don't have any of this, we now have to employ platinum here to act as our electrode. So it's like if there's no man of the house, then you have to get the man of the house there. Then, so platinum. Then this side, obviously, our Au is the solid, so it's the man of the house of the cathode here. So that acts as the electrode. So here we have our cathode, and then here we have our anode, right? So this is the anode electrode, and this is the cathode electrode, right? So when you write your cell notation, you have to consider that you used this platinum as your electrode. Because remember, every time you write a cell notation, it must always start with the electrode, the anode, and then goes to whatever ions that you have here in the electrolyte, and then Sol bridge, and then you have the ions that will be in here on the cathode, which is your Au3+, that are being reduced to Au here. So the cell notation would look like this. You have to be careful. So that's PT and then solid. And then what do we have on the half cell there? That's Cl minus in aqueous. But then remember, again, we have chlorine gas here. So we need to say phase change. Remember the Cl minus, we are saying that it is being oxidized to Cl2, right? So Cl minus is being oxidized to Cl2. Now that means this one is in gaseous state. And then we have our Sol bridge now. Sol bridge is indicated by double arrow, like a double slash. Then we have Au3+ in aqueous. And then again, we have Au as our cathode, and then it's in solid. So make sure that you understand this type of cell there, right? So it's not very common, but then you can just go back to questions on, go back to exam papers that were written in 2018, 2019, 2017. You are going to find questions like this. Okay, so That's the cell notation. We have calculate the standard reduction potential of AU. Now, why are they making you calculate the standard reduction potential of AU? Let's go here. You will understand that AU is not given, right, in the standard reduction potential. So you can check it from up here all the way down here. You won't see any AU here, which is why they want you to calculate it, right? So now, what are you going to do in terms of calculating that? So you know that your formula, it is still E cell is equals to E cathode minus E anode. Now, up here, we are given that the initial reading on the voltmeter is 0.14. So that's your E cell, 0.14. Now, we did mention that this is the cathode. We don't have the AU, so let's just put X there. But then there is a way in which we can find the anode. The anode is the chlorine here. Also, you can find PT. So PT is only there for the purpose of acting as an electrode, but then it does not take part in this whole reaction here. The reason, in fact, we are using platinum, it's because it's inert, it's unreactive. So it won't change the concentration of the electrolyte. So if they do come up with that question, why are we using platinum instead of any other metal? It's because platinum here is inert, so it won't oxidize there. So if it were to oxidize, that means it would affect the electrolytes here. But then now, because it's inert, it's unreactive, it won't affect the concentration of the electrolyte of the anode side. So, but then we can find the anode by checking for Cl2 and Cl minus. And then looking at this one down here, we can see, there we go there. So let's highlight that. So there we go. Right, so 1.36. 1.36. So minus 1.36. And then now to calculate X, let's just transpose the negative here. 0.14 plus 1.36. Then if you add the 2 there, you are supposed to get 1.5 volts, right? So therefore, in other words, the reading for AU is 1.5 volt, right? Now, obviously, you cannot match it up with anything there because, as I said, it is not there. So you were just trying to calculate the reading. So also pay attention to this kind of questions here, because not all these questions are just straightforward, whereby you have to calculate the E cell. Sometimes you are given the E cell, and then you have to calculate the reading of the elements there, right? So, okay, nice. So that was a pretty interesting question right there. Then what are they saying? Are we done? Okay, 12 marks in the bag. Let's go to question 9. So question 9, electrolytic cell. Now, electrolytic cell, the simplified diagram below represents the electrolysis of a concentrated sodium chloride solution. The balanced equation for the reaction taking place in the above cell is this one here. So 9.1 says define the term electrolysis. So what is electrolysis? We say this is the chemical process. The chemical process whereby electrical energy is converted to chemical energy. Right, to chemical energy. That's it. So the chemical process whereby electrical energy is converted to chemical energy. Okay, then 9.2 says which electrode is the anode? Now you will remember that the anode should always be the positive terminal and the cathode should be the negative terminal. The reason for this is because electron flow is from anode to cathode, but also current flows from the positive terminal to the negative terminal, right? So which is why it's like that. And then which one is the anode? The positive is always indicated by the longer terminal there. And then this one is the negative. So it has to be what? X. So 9.2 is X. Then 9.3 says write down the half reaction that takes place at electrode X and electrode Y. Now this one also, it's a very interesting one here. So it's not like any of the other cells here, because as we can see here, we have NaCl and then we have H2O. So we have two of this reacting. They are trying to do an electrolysis of the concentrated sodium chloride solution. So they have to add water there. But then in most of the cases, we know that our sodium here acts as a spectator ion, right? So what we are seeing from this reaction is simply 2Cl minus to give us plus 2H2O. And then this is 2OH minus plus H2 plus Cl2. If we remove the spectator ions there, sodium. So that means sodium has nothing to do with this reaction here. What we are simply looking at is the Cl minus here, and then also the H2O. Now at this point, it says write down the half reaction that takes place at electrode X. We have identified that electrode X is an anode. So that means electrode Y is a cathode. Now in the anode, if we refer to red cat and ox, we know that in the anode, we should have oxidation taking place. And then in the cathode, we should have what? Reduction taking place. Right. Now looking at this oxidation, we are expecting an increase in oxidation number. So moving from a negative to a positive. If we look at Cl minus here, it had a -1. And then now it has what? 0 here, because it's now a diatomic atom. Molecule, meant to say. The -1 is to 0. That means we have oxidation taking place here. That's an increase in oxidation number. So that means electrode X must be the one that shows us our chlorine. Now, where are we going to take that one? It is there in our reactions there. It's the same one that we used. So the Cl2 to 2Cl. You see how it appears exactly as that one. And because we say this is an anode, we know that we should write it like this from the right to the left. We should flip it. So that means for electrode X, the half reaction that we are supposed to have has to go as 2Cl minus, and then to yield Cl2 in gaseous state plus 2 electrons. So we lose 2 electrons there in order to come out to this, right? So note that the 2 here is coming from here, because if we have Cl minus and then now there's 2 of the Cl minus, that means how many electrons do we lose? 2 electrons. So this will be your electrode X. But then what about electrode Y? Electrode Y now has to be indicated by this, right? Has to be indicated by this. Now we do have a reaction of H2O to give us 2OH minus plus H2. You're going to find it from this table, right? So everything that we are dealing with here, you have to check if there is no such formula here. Look. Somebody come and look at this. Then 2H2 plus 2E to give us H2 plus 2OH, exactly as it appears here, right? So that means electrode Y has to be 2H2. Remember, with the one that is reduction, you just simply write it exactly as it is. So you don't have to flip the equation, because these are standard reduction potential. So everything in here has been written in the format of reduction. And then this is your H2 gas plus the 2OH minus. So exactly as it appears there. Right, so that means in electrode X, that's what you have. That's your anode. And then here, that's your cathode. Right, now, if you can check here, you can see that there's an inverse in this. We said this one is the anode, and then this one is the cathode. always, that's the case. That's why when we want to calculate the EMF here, we always find it as a negative, because now it's no longer working the same way as the galvanic cell. If you are still using your 4B, that means the cathode has to be the one that appears first, and then the anode has to be the one that appears second, right? So it's much more of an inverse to what you have in your galvanic cell. In galvanic cell, the one that appears the first is the anode, and then the one that appears the second is the cathode. But right here, you have the cathode appearing first, and then the anode being the one that is down there. So which is why some of your teachers, they tell you that if you are working with your electrolytic cell, it is best to use your 4A table, right? So that you still maintain that your anode is up there, and then your cathode will be down there, right? But then if you are still using 4B, you have to note that it's now inversed. So I hope that makes sense there. Okay. So also these questions here were more of questions from 2017, 2016 back there, right? You never find such questions after the COVID year, right? But then they kind of brought it back right now because remember, you have your full curriculum in full force right now. So you might just as well do yourself a favor to kind of go back to those questions and practice with those older question papers. Okay, then we have 9.4 for 6 marks. We are always expecting that kind of calculation right there. A current of 0.5 amperes is applied over a period of 5 hours. Our time is given in hours, but we know that our time should be in seconds. So we need to convert it to minutes first, and then from minutes to seconds. So that's times 60 times 60, right? Then calculate the volume of chlorine gas at STP. So STP, we know that whenever we see STP, the formula that should come to mind is N is equals to V over Vm. So somewhere we will have to apply that formula there. That is formed during this time. Now, this is a reverse calculation, of course, because most of the time we are used to having to calculate the current. So right now we are given the current and we should calculate the volume, meaning we should work this question backwards by saying that we know that our current is Q over delta T. But then the first thing that we are going to calculate is our charge. We are given our current 0.5, and then we are given our time 5 hours. But then the 5 hours there should be written in terms of seconds, which if you say 5 multiplied by 60 multiplied by 60, it should give you something like 18,000. Then when you cross multiply there, your Q is 9,000 coulombs, right? Now from here, you need to then use the formula. So number 2, you want to say N is equals to Q over E, right? We are working at it backwards. And then this is your N is supposed to be, so that's what we are trying to calculate, 9,000. The E here is the charge on electron, which should always be substituted as 1.6 times 10 to the exponent of negative 19. In your data sheet, it appears as a negative, but because your N here should always be a positive integer, you will have to substitute it as a positive. So note that. So N is equals to 5.625 times 10 to the exponent of 27 electrons, right? Electrons. Now, from here, you can try to then calculate the number of moles of the electrons. So number 3, you want to then calculate the number of moles of the electrons. So note there is a difference between this end here and the end that I'm going to use right now. All these two formulas, 1 and 2, are from your paper 1, right? Physics. So this is a current formula, and then this is a formula from Coulomb's law to calculate number of electrons. Then here, I'm simply calculating the number of moles. So this N has a different meaning now. So at this point, I can say I have This is not the formula I want. Actually, N over NA. Yes. So here I'm trying to calculate the number of moles. The N here, number of electron, is similar to this N here in paper 2, right? Because this represents either the number of moles, the number of atoms, the number of molecules, or the number of particles. So the N that you are seeing from here is the same as this big N here from paper 2. So that means I will have 5.625 times 10 to the exponent of 27 divided by the Avogadro's constant, which is 6.02 times 10 to the exponent of 23, right? So we know this formula N is equals to N over NA. So we're looking for this number of moles. Now, when we calculate that, we find that our number of moles are 0.093 mole, right? But then we want the volume of chlorine gas. So what are we going to do there? From here, you will remember the reaction that we gave out in electrode X was the one that says 2Cl minus, and then to give us chlorine gas plus 2E, right? Remember, these are the number of moles of the what? Of the electrons. But what are we looking for? We are looking for the volume of chlorine gas. So now we have to compare the ratio of the electrons to the chlorine gas. And then we find that the ratio is what? 2 is to 1, because there are 2 electrons, but only 1 mole of the Cl2, right? Then this is going to be 0.093 is to X, right? Then if we cross multiply here, this is just 2X is equals to 0.093. Then divide both sides by 2. Our X is going to be what? 0.0465 mole, right? But then now we want the volume of chlorine gas. That means that the final formula that we have to use now is this one. N is equals to V over Vm. So from here, you want to come and use this formula. N is equals to V over Vm. Now the number of moles, 0.0465. You are looking for this volume up here. The Vm is a constant. The molar gas volume at STP, it is there on your formula sheet. It is always 22.4, right? Then if you cross multiply here, your volume is 1.04 dm cube, right? So that's how you were supposed to go about answering that question. So it's a pretty interesting question there. So, but then with more practices on that, you should be able to get that question there. So I will also upload some of the videos there concerning this question and how you go through the steps of finding questions like that, right? But then we have came to the end of the question paper with that. So this was for a whopping 13 marks. And then if you make sure that you practice that calculation, because that's the only thing that might be a bit of a challenge when it comes to electrolytic cell. So if you just make sure that you practice that question very well, then that's the 12 marks plus the 13 marks, that's 25 marks in total. So that's a very decent marks if you're going to add them to the 50 plus marks that you got in your organic chemistry, right? So you are somewhere around 70 something, 75, and then that should be half of the question paper there. So that's your 50%. Now, if you go back and you try to get those questions from your acids and bases, and also you grab some of the marks from your reaction rate and chemical equilibrium, you can walk out with about 105 marks, which should put you at about 70% of the question paper. So have a strategy, have a goal when working with your exam paper, and then always have an aim there, and always know where your marks are, right? But then with all that being said, please press the thumbs up button if you have enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please, please, please hit the subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.